So, for a particular prospect, how do we know ahead of time what the best parameters should be for the overall survey size, the line direction and line spacing, the CMP interval, and the group interval?
We quantify what we already know about the geology, velocity, and structural dips in the area by determining the Fresnel zone radius, the spatial aliasing, the maximum migration aperture, and the minimum migration aperture. First, let's determine the Fresnel zone radius for a prospective horizon. We remember that the total observed energy actually comes from an area of reflection points in the subsurface. The Fresnel zone defines the size of this reflection area, and we need to know the size of this zone in order to be able to properly focus reflections. The radius of the Fresnel zone is equal to 1/2 the RMS, or root mean squared, stacking velocity, down to the horizon, times the square root of the two-way travel time to the horizon, divided by the frequency of the seismic data at the horizon. Next, let's compute the spatial aliasing frequency for the prospective horizon. We'll use this value to select the sampling rate, the spacing between survey lines, and the optimum CMP interval spacing, critical factors in the cost of the survey. When we sample a wave, our results may be ambiguous. For example, is this a wavelength of 50 or 200 Hertz? We call this ambiguity in sampled data aliasing. To prevent aliasing, we must sample a wave at least twice for each cycle of the highest frequency present in the waveform. In seismic work, we typically require 3 samples per cycle. To determine the aliasing frequency at a horizon, we need to know the RMS stacking velocity to the horizon, the horizontal interval spacing, in this case the CMP interval, and the structural dip. For example, if the velocity to a horizon is 3,000 meters per second, the CMP spacing 50 meters, and the horizon structural dip 20 degrees, then the spatial aliasing frequency is 44 Hertz. We can also create a table entering the expected range of structural dips and different CMP spacings. By estimating a velocity to the prospective horizon, we can calculate the spatial aliasing frequency in Hertz. This table and formula will help us determine the aliasing frequency for structural plays. But what about stratigraphic plays, in this case a channel sand, in areas of shallow dip? Survey lines must be close enough together to produce at least 2 or 3 CMP samples within the lateral extent of the play. Generally, the CMP interval spacing ranges from 10 to 50 meters, but we must be sure to sample the subsurface adequately, based on the expected size of our play. The third parameter, maximum migration aperture, describes an area, also called a halo or padding zone, around the perimeter of the survey. We must include this area in the survey so that edge effects, caused by the migration process, will occur well away from the prospect. We only need to consider dips perpendicular to the margin of the prospect, provided that steep dips toward the center of the prospect are migrated properly. If the steep dips over the center of the prospect cannot be migrated properly, or if there are steep dips around the survey edges, then the survey area is probably too small. This geometric construction shows that the maximum aperture distance, Xmax, depends on the structural dip and the distance to the horizon, which can be defined in terms of the RMS velocity and the two-way travel time. For example, if the velocity is 3,000 meters per second, the two-way travel time 1.8 seconds, and the dip 20 degrees, then the maximum aperture is 923 meters. We must include this additional distance in the survey to limit migration edge effects. The fourth and final parameter to determine is the minimum migration aperture. This value tells us how far we need to extend lines in order to get proper full-fold migration over the prospect and a satisfactory seismic response in areas of zero dip. In practice, we compare the minimum and maximum apertures and use the larger value, which may be on the order of a kilometer, to extend the overall size of the survey. But there are 2 additional parameters we need to know before we go out into the field: the overall cable length and the near group offset. The cable length should be at least equal to the depth of the deepest horizon of interest. The near group offset should be less than 2½ times the distance of the group interval, and less than the depth to the shallowest horizon of interest.